All right, AP, this is sample exercise 3.62, determining a molecular formula. Caffeine, a stimulant found in coffee, tea, chocolate, contains 49.48% carbon, 5.15% hydrogen, 28.87% nitrogen, and 16.49% oxygen by mass, and has a molar mass of 194.2 grams per mole. Determine the molecular formula of caffeine. Go and press pause now because here comes the solution. We first determine the mass of each element in 1 mole of caffeine. In remember, we've already been given the molar mass of caffeine as 194.2 grams per mole. The percentages, the percent of carbon was 49.48% carbon, so per 100 grams sample of caffeine, 49.48 grams of its carbon. We can combine conversion factors to make this a little bit more streamlined. So if we multiply the mass of caffeine by the molar mass of caffeine, we get the grams of carbon per mole of caffeine. Notice we are multiplying. We're not actually canceling. Well, we are canceling a little bit. We're canceling a gram, one of the grams. But aside from that, we're not canceling much. We still have a gram and we still have carbon. Notice over here we have grams of carbon. We still have caffeine. And over here we have moles. So instead of the grams of caffeine being our unit, or the grams of caffeine entirely canceling, just the gram is canceling. So our unit on the denominator here is moles of caffeine. So that's how you see that we generated per mole of caffeine for each of these values. But again, mass of hydrogen per 100 grams of caffeine. Take the molar mass of caffeine as a conversion factor. We get 10.0 grams of hydrogen per mole of caffeine, 56.07 grams of nitrogen per mole of caffeine, then 32.02 grams of oxygen per mole of caffeine. And so we have grams per mole of caffeine. And we're going to take each of these values and do another conversion. It's simply going to be the molar mass of each of those elements. So for carbon, we generated a 96.09 grams carbon per mole of caffeine. We're going to take that and use a conversion factor of the molar mass of caffeine. Notice that the grams of carbon cancel right here, and so our units are going to be moles of carbon per mole of caffeine. So for carbon, we have 8.00 moles of carbon per mole of caffeine. For hydrogen, we have 9.92 moles of hydrogen per mole of caffeine. For nitrogen, we have 4.002 moles of nitrogen per mole of caffeine. And then for oxygen, we have 2.001 moles of oxygen per mole of caffeine. Now, because these are so ridiculously close to whole numbers, we're not necessarily rounding here. What we're recognizing is that our precision here is limited by the number of significant figures that we're using. I mean, the number here with the absolute largest number of significant figures is the one that that we pulled out. Is that 4 significant figures? We have 4 significant figures, 3 significant figures, and so we're limited to 3 or 4 significant figures here. That's not all that precise if we're trying to get exact, should I say exact numbers. 8.001, that's pretty darn close to 8. And if we didn't have to round because of certain significant figure limitations back up here, these actually would be 8, 10, 4, 2. And so rounding the numbers to integers gives the molecular formula for caffeine. C8, H10, N4, O2. Now, in general, this is a different way of going about a molecular formula determination. Okay, you can go through that normal step. Okay, we were given the mass percent per each element. Turn that into a mass, turn that into moles, and then relate each mole value to each other mole value by dividing all of the mole values by the smallest mole value present. And those will be the subscripts for those elements, that works. This is simply another way that involves a little bit more conversion factor action to generate the exact same data.